first postdoc in Marseille at the Laboratoire d'Astrophysique de Marseille, where he worked with Sylvain Delatorre on redshift space distortions. And he then arrived 2 months ago at our institute to work mostly on Euclid and DESI. And today he will talk about the distance redshift relation in an homogeneous universe. So I now ask Michel-Andrès to share his screen, and the floor is yours.
Thank you very much for the introduction. So for this seminar, we'll talk about the distance redshift relation in an inhomogeneous universe. And actually, at first, I would like to recommend this very pedagogical paper from Hogg. Actually, it's not really a paper, it's in quotes. It's more of a small research note, but still, it's a very useful way to start to understand this concept of distance in the case of homogeneous cosmology. So it's a very good introduction. So in cosmology, we have different definitions of distance, which relate to very different aspects. So first, we can think about what we call the co-moving distance. So this is pretty much the distance between two events, as if we could measure it with a very, very long ruler. So it's some kind of instantaneous distance between two events. And actually, it's, I think, one of the notions of distance that is the most commonly used, especially when, for example, we need to correlate some statistical properties with the separation in distance. So the co-moving distance is the first thing. Then we can also see the angular diameter distance. So actually, this is just the distance that relates the physical size of an object to the angle under which it is seen. And last, we can see the luminosity distance, which just relates the luminosity of an object and the incoming flux. So for this seminar, when I will talk about the distance redshift relation, I will be discussing actually of the last two definitions of distance. But actually, when we are in the case of a homogeneous universe, actually all these notions are related by very simple relations. And actually, even if we are not in a homogeneous universe, in general, the luminosity distance and angular diameter distance are related with this also very simple relation called the distance duality relation. So this should hold in principle even for the case of an inhomogeneous universe. Actually, from this, we can actually see that the relative perturbations on the angular diameter distance and luminosity distance are the same, and we can actually drop the subscript. So actually, during the seminar, when I will discuss about perturbations on the distance, it doesn't really matter if I'm discussing about the luminosity distance or angular diameter distance, because the relative perturbations are exactly the same. So now we can wonder, well, why are these notions of distance actually important in cosmology? Well, they are important because they relate to very important observables that we use to constrain the nature of our universe. For example, we can think about the cosmic microwave background, for which we extract the information from the anisotropic temperature fluctuations correlated at some given angular scale here. And of course, since we correlate fluctuations of temperature at some angular scale, this the related notion of distance is the angular diameter distance. And also on the other side, we can think at low redshift, we can think about the Hubble diagram, for which we have a measure of luminosity and redshift, and which is very important for us to constrain the parameters of our universe. And this notion, which relates luminosity and distance, is the luminosity distance. So actually, the question is, in the case of a real inhomogeneous universe, as the one that we have, is the averaged distance equal to its homogeneous counterpart? It's important because in general, in different analysis, when we the model that we use is based on this homogeneous universe. So said differently, now I will introduce this small letter d, that is just a ratio between the distance in an inhomogeneous universe divided by its homogeneous counterpart, is this average measure of distance equal to 1. And actually, this question regarding a very long history, like starting from the 60s and with Zel'dovich, where at the time he considered the case of an Einstein de Sitter universe. So we have all the energy content in form of matter. And he made it so that if all the mass was in form of clumps, like what we have here, and this means that we have perfect void outside of these clumps, then photons in principle should propagate mostly in completely empty regions, like what we have here. And in this case, well, due to gravitational lensing, the size of light beam should the light beam should defocus during their propagation, which means that on average, in a real inhomogeneous universe, the measure of distance should be superior to the one that we would have in the case of a homogeneous one. So this measure of distance is called the empty beam distance, and it's pretty much an upper threshold on the possible effect of gravitational lensing on the measure of distance. Of course, at the time, this was a very simple model to try to understand all these different effects that could impact the distance redshift relation. But still, this model was further improved in the following decades, like allowing for different cosmological models, also allowing for the fact that maybe we don't have all the mass in form of clump, but only a fraction. But still, the main idea of this paper is that we cannot interpret cosmological data using just the distance redshift relation of a homogeneous universe. Or if we do that, we would have bias in the estimation of cosmological parameters. But then actually, there was a lot of progress regarding this kind of model. But then, since this paper from Weinberg in '76, he actually proposed that, he actually showed that the average distance, even if we have an arbitrary distribution of point masses, should be the same as in the case of a homogeneous universe at first order. So what this means pretty much is that we should, even if we analyze data from an inhomogeneous universe, it should be roughly the same as in the homogeneous one, even in the case of strong lensing. So this was at the time a very powerful statement because it's completely against what was said previously. So this was the first part of this very interesting paper. The second part, actually, he uses some kind of conservation argument, photon conservation argument, where he shows that in all generality, actually it's the inverse of the distance squared that should be conserved, even in the case where we have an inhomogeneous universe. And actually, the demonstration goes like this. So pretty much, if we imagine that we have a source that emits n photons per unit of time, then in a homogeneous universe, when the photons reach some given redshift, we should have a flux that should be equal to the number of photons just divided by the area at the constant redshift surface, which is proportional to the angular distance squared. In the case of an inhomogeneous universe, if we have the same number of photons, meaning that we have a transparent universe here, the mean flux should still be proportional to the number of photons divided by the area. And now the very important conjecture is that if the area of the constant redshift surface is not affected by inhomogeneities, that if it's the same in a homogeneous universe and in inhomogeneous universe, then the flux is also the same, meaning that the ratio of distance squared should be equal actually. So this is pretty much what he said previously. But actually, there is a big problem here, is that actually all of this is just well, a reformulation of the whole problem, because now we say that the inverse distance squared is the same as in a homogeneous case, but we assume that the area are equal. So now the problem is, well, whether or not this is the case, and this is what we will see later. So this paper was really important because it really showed that at first order we could still use the formula from a homogeneous universe even when analyzing real data. So for years it continued like this, and actually very recently there was this paper from Clarkson et al., which well, showed that actually the average distance is biased with respect to its homogeneous counterpart, and there is this additional term which comes from gravitational lensing. And this term is supposed to be small enough. But the idea of this paper is that actually, if we integrate this term over a long period of time, or up until a very, very high redshift, then it could become non-negligible. This is pretty much what they show here. Here they show the effect of this term. And well, when we are at low redshift, it's negligible. But when we reach a redshift of roughly 1000, which would be well, very close to the cosmic microwave background, then we should have a percent effect. And having a percent effect on the angular diameter distance on average, they say should impact the position of the baryonic acoustic oscillation, of the position of these peaks, and which means that it should impact severely the estimation of cosmological parameters, and this is what they showed here. If we don't account for this correction, but we have the standard estimation where we have the Hubble parameter value up to 78, pretty much. And if we account for this term, well, we have a shift of the cosmological parameters, which, well, agrees much more with low redshift estimation. So this was the main idea of this paper, that if we have this term integrated over up until a very high redshift, it can impact the cosmological parameters. So it's a very interesting idea, but actually it was refuted later, partly also by the same team. And I think it's very interesting to see why this was refuted. And actually, the next 3 slides will be a little bit technical, so we need to focus here, but then it should be a little bit easier. So, and actually, there is this paper from Kaiser and Peacock, which try to really show why this cannot work, and it goes like this. Actually, there is a big difference between different averaging procedure in cosmology, namely what we can call source averaging and direction averaging. Like in the first case, if we think about direction averaging, let's say that we put galaxies in random directions in the sky. Then we have this kind of picture, and over here we can average over different random directions. But the problem is that when we observe distant sources, we do have effects of gravitational lensing, which make some regions in the sky larger, or some region in the sky in the sky smaller. For example, here we have a magnified region, which takes more space, and here we have the magnified regions. So this is pretty much what we would observe when we have, let's say, a galaxy survey or even supernovae. So here the idea is that, as we can see, if we average over some random sources here, we should have a different result than when we average over random directions. And actually, these different averaging procedures depends on which kind of observable we are considering. So if we are considering galaxy survey or supernovae, for example, we are in the case of source averaging. And in this case, the mean distance is superior to the one of a homogeneous universe. And here we recover the result of Weinberg, that the inverse distance squared is roughly equal to the mean magnification, which should be roughly equal to 1. But actually for the CMB, well, we have photons that come from every direction in the sky, and which means that in this case we are averaging over directions. And when we are averaging over directions, actually the mean distance is lower than in the case of a homogeneous universe. In this case, it's the distance squared that is roughly conserved with respect to the homogeneous case. So first, here we can see that for the CMB, the distance is decreased. So this is not what we had here. So this is just a first, just a first correction. But actually, it's not the main one because, well, even if it's a factor 1/2 instead of 3/2, well, it could be important here. No, the main argument of this paper was that actually the CMB analysis is not sensitive to the mean distance, but to the mean distance squared. Actually, it's very different because the averaging procedure is not commutative. And maybe just to understand a little bit with the hand what it is the case, it comes from the fact that here, let's say that we have an observer here. This is the past light cone. And in gray, we have a constant time hypersurface. So this is just a slice at the last scattering surface. So for us, the CMB and the BAO is just an angular scale on the sky. So this is what this theta star. But this maps up to some physical size on the last scattering surface. So this is the sound horizon. And actually, when we want to know what is the position of this BAO peak, we're asking how many times can we count this sound horizon on the last scattering surface. And the number of times we can count this portion of area on the last scattering surface depends on the area of this surface, which means that it depends on the area which is proportional to the distance squared and not the distance. And actually, as we have seen here, the mean distance squared when we average over directions should be equal to 1. So there should not be any strong impact of inhomogeneities. And actually, what they try to see also in this paper is, well, to which extent do we have this mean distance squared is roughly equal to 1? And by this, they try to, well, close the loophole of the argument of Weinberg from 40 years ago. And they say that we can distinguish two kinds of effects which can modify the constant time surface, the area of this constant time surface. First, because in a real universe, photons do not propagate in straight line, if we are at constant distance traveled, for example, here we have a photon that propagates in straight line. Here the distance reached is the same as the distance traveled, but now in an inhomogeneous universe, photons do not propagate in straight line and therefore will reach a smaller radius if we have the same distance traveled. Since it reaches a smaller radius, it means that the overall area is decreased. So just this is what we call the Wiggly ray effect, the fact that there is the area of the surface decreased because photons do not propagate in straight line. But then there is a second thing. Due to time delay, actually, when we are at constant time, photons can propagate farther from the homogeneous case, or maybe stop a little bit before. So this is just due to time delay. And this will cause the area, the surface, to have wrinkles. And these wrinkles will actually increase the total area. So this is what we call the Wrinkly surface effect. So here we see that there are two competing effects: the fact that photons do not propagate in straight line and therefore reach a smaller radius, and the fact that due to time delay there will be wrinkles in the area, and this will increase. And the main result of this paper, and this is the analytical calculation that they have made, is that at the CMB, the perturbation of area should not exceed a relative value of 10 to the minus 7, 10 to the minus 6. So they say that we should not have here any problem for the analysis of the cosmic microwave background. So from here, actually, we tried with a collaborator to verify these numbers and also try to go further this work from Kaiser and Peacock. So what they have done is that they have done a fully analytical work in the weak lensing regime. So also assuming that all the standard gravitational lensing quantities were small, they used linear theory, and they also only accounted for the impact of gravitational lensing. So recently what we have tried to do is that we have tried to generalize this kind of analysis, but using numerical simulations, meaning that with high resolution numerical simulation, meaning we have access to the very nonlinear regime of the formation of structure. We account for weak and strong lensing. And also, just beyond gravitational lensing, we account for all the different contributions that can arrive at first order in metric perturbations. This is really because there was this argument that maybe there could be an important contribution from the very small scales, which well, we cannot model properly with simple analytical work. And well, the main results we try to show and try to study is first testing the distance-redshift relation, meaning that when we have different kind of observable, do these relations really hold, meaning for source averaging and directional averaging. And then I will show some results regarding Weinberg's conjecture, so that is the distance squared when we average over direction almost 1, same as the inverse distance squared when you average over direction. So this is what I will try to, so this will be my focus for this talk. And to do this, we really need to use n-body simulations and ray tracing method where we follow the propagation of light rays within these simulations. So here is just a slide to briefly present the simulations that I use. So we use what we call Newtonian n-body simulations of dark matter. Here we have the main characteristic of the simulation. So we have 4,000 cube particles with a 2.6 gigaparsec box size. So these simulations are quite similar in terms of size and number of particles as the MICE Grand Challenge 1. And for this, we have made simulation with different cosmologies, but for this seminar, I will focus on the lambda CDM one, which is, well, just the concordance model in cosmology with dark energy with a form of cosmological constant and non-relativistic called dark matter. So from these simulations, we can output some light cones. So here we output 3 different light cones with different depths and aperture. So a full-scale light cone up to redshift 0.5, and then narrower light cone up to redshift 2 and redshift 10. And for this analysis, since I'm interested also, I'm interested in the low redshift regime and also the high redshift regime. Actually, I will analyze all these different cones, all these different light cones, and show the results of the concatenation of these different light cones. From the simulation, so we output the light cones containing, well, different dark matter particles and dark matter halos, but we also have the information of on the gravitational field. And since we have information on the gravitational field, we can perform ray tracing within these light cones. So what we do here, our approach, is to directly integrate the null geodesic equations for photons within the 3D adaptive mesh structure of the simulation. This means that we really account for the very high density regions, very nonlinear regions of the simulation. Since I'm interested in different kind of averaging procedures, so directional averaging and source averaging, I also need to produce different observables that relate to this different averaging procedure. And to do that, I use hill peaks so that I can pixelize the sky and launch light ray in the direction of these pixels. So with this, we will have our observables for directional averaging. And then to have source averaging, what we do is that, for example, we detect some halos on the light cone. And then what we try to do is that we integrate the trajectory of photons starting from the observer today, so we integrate toward the past, and we try to find the null geodesic that connects the observer here and the source. So what we do is that at first, since we know the co-moving position of the source on the light cone, we first launch a light ray in the direction of the source. But the problem is that due to gravitational lensing, well, the ray will not hit the source, and it will because it deviates during its propagation. So what we do is that we integrate over the initial conditions of the light ray to find the initial condition which makes the photon hit the source. And when we have that, then we have all the necessary information to compute all the different distance measure. So here with this ray tracing method, we can produce direction observable for direction averaging and also for source averaging. Okay, so now I will directly show the no, just after. Okay, so the idea is that if we use these ray tracing techniques, actually we can account for a lot of effects at first order in metric perturbations, and this goes much beyond the previous analytical work, which only accounted for weak gravitational lensing. And of course, all these different effects that we can see have a distinct imprint on the distribution of the observed distribution of matter. Okay, so now I will show the results. So first, I will focus on the distance redshift relation on the impact of inhomogeneities on the mean distance. So first, when we see in the case of direction averaging, which means that in the case where we are interested in the direction average over some maps, we find actually this. So we find that for a wide range of redshift, our data points actually agree very well with the theoretical, with the second order theoretical prediction, which predicts that in an inhomogeneous universe, the mean distance is lower than in a homogeneous one. So this is the first thing. Then when we look at the average distance in our halo catalog with this method where we really find the null geodesics between observer and sources, then we see that actually in this case the mean distance is increased with respect to the homogeneous case. So here I show the distance in blue, the mean distance in blue, and in orange I show the distance modulus. I just show it because it's also used in observational analysis. So actually it's very nice here that we can see that in both cases for these two different observables, we can clearly see this trend that that we could expect from the effect of gravitational lensing at second order. But it also shows that it's important to really distinguish between these different notions of averaging when we want to be really precise with the interpretation of these measurements. Okay, so this was for the measure of distance. Now, when we look at here, it's a measure of the distance squared. We see that actually it's very close to 1, up to 1 per mil, pretty much. when we average over direction. And when we average over sources, we have the inverse distance squared that is almost equal to its homogeneous counterpart, same up until 10 to the minus 3. So here it seems that for the moment we can really recover very well the theoretical prediction, the second order theoretical prediction, which only accounts for gravitational lensing. Even if here in this case, actually we have the fully nonlinear case, we account for all the different effects at first order geometric perturbations, we can still very well cover what was expected. But actually, when we go a little bit deeper and we study a little bit more in depth the effect of area perturbations, well, first we can see what happens with the Wiggly ray effect. So remember, it's just the fact that due to the propagation of light, and because light will not propagate in a straight line, light will generally reach a smaller radius at some fixed distance traveled. And so this is what we can see here. So of course here we have the data points. The dashed line is the previous calculation from Kaiser and Peacock, and in a solid line, it's an updated prediction that we have done, but it's just that it's pretty much the same as the dashed line, but with much less approximations. But in any case, we see that it agrees extremely well with the theoretical prediction. And also maybe another thing that is interesting to see is that the effect, this Wiggly ray effect on the area is extremely small, right? A few 10 to the minus 8 on the relative perturbation. So this is just, so this was the Wiggly ray effect. Now this is the Wrinkly surface effect. So the fact that due to time delay, there are wrinkles on the constant time surface. And actually we have used a different method to compute these wrinkles because it's not really straightforward, but we see that they seem to agree quite well with also the previous theoretical prediction here. So I must say that when I saw this result, I was very surprised because these predictions, which are well, not straightforward nor trivial, but still there are a lot of approximations. These predictions seems to agree extremely well with even our fully numerical investigation. So it's very interesting to see. So for the moment, we have the same result. The only difference is that for us, we accounted for the fact that when we are at constant time, you could have a mean shift of the value of the radius reached. And in this case, well, we mainly have a very high scatter, but actually these very large error bars, of course, they agree with 0 roughly. But these error bars are mostly due to the fact that we have very narrow cones, and these quantities like time delay, they depend on very long range modes. So this is why we have very large error bars. But still, we see that actually the size of these error bars of 10 to the minus 5 is in any case much larger than this very subtle study on the wrinkle surface and Wiggly ray effects. So from this, I will actually conclude. So I think that the main takeaway is that yes, the distance redshift relation is biased with respect to a homogeneous universe. And here I can add, and also this bias depends on which kind of averaging procedure and which kind of observables that we are considering. Overall, this is well modeled at high redshift by the effect of gravitational only, so just the calculation at second order. And for us, at least we can confirm Weinberg's conjecture up to 10 to the minus 5, which means that there is no problem for the CMB. And just maybe for the Hubble diagram, when we are at very high redshift, we might account for this bias. but this is a possibility, or else when we build the Hubble diagram, instead of using distance modulus or distance, luminosity distance, maybe we can just use the 1 over d squared, which is well, non-biased at the 10 to the minus 7 level. So this is just something. And okay, so last there are some perspective to this work. In our case, well, we have a simulation which have some limitation in mass, and in our case, we do have strong lensing effects, but we still have galaxies as deflector. I just wonder what happens when what if we had even more resolution, and what about macro lensing? Maybe we would have more strong lensing events, and this would bias even more our results. This is the first limitation, and then we assumed that we had a transparent universe, meaning that even when photons crossed halos, they were not really stopped, right? They just continued. So maybe I would also like at some point to investigate the effect of blending on these measurements. Okay, so thank you very much.
Thank you very much, Michel-Andrès, for your talk, and also for being perfectly on time with your 40 minutes long talk. So I think now we have time for questions or curiosities. I think, okay, we have one raised hand. So yes, Enrique, you can unmute yourself and ask for the question.
Hello, Michel. Thank you very much for this interesting talk. Can you hear me?
Yes.
Okay. Well, my question is regarding the first paper by Clarkson before the Kaiser Peacock revision. I was wondering the fact that when, for example, to estimate H naught and omega matter, people, the CMB Planck team took into account the weak lensing distortions to the power spectrum. And I was wondering if this is part of this picture or not. What is the impact of this weak lensing effect?
Yeah, no, actually it's a very good question, because there are mainly, I would say, there are two effects of gravitational lensing. The effect that is usually accounted for, and rightly so, is that lensing induces a damping of the amplitude of this BAO. So this is accounted for, and this should, right? So there is no problem. Here, the idea was, it was about a shift on the value, a shift on the BAO peak, pretty much. What does the relation between multipole and and distance? And here the idea was that maybe, since the multipoles are related, the angles are related to some scale, if on average the related distance is different, maybe also we should shift the multiple the multiple scale. And
Okay.
so this was the idea. And here, like, maybe there could be like a 1% shift on the multiples and on the position of the BAO peak. And so this was the idea. So this was not accounted for. And here they just tried it. I mean, they just tried it, but as I said, so this was there was a revision from Kaiser and Peacock, but also there was a revision from 1 year later by also the same team, which actually saw that well, the idea was interesting, but it was a little bit naive. And actually, the most difficult part was to see that the position of the peak and the shift on the BAO peak does not depend on the average distance, but on the average distance squared, which this one is almost unbiased. So this was the main difference.
Thank you.
Okay, I see another raised hand by Pablo Fosalba.
Hi, Michel-Andrès. So very nice talk. I wanted to ask you something which is related to your topic, but it's slightly different. So probably you have followed this discussion that there was a few years ago on the impact of the growth, the nonlinear growth of inhomogeneities in particular, on the expansion rate of the universe. So whether what is called back reaction from this nonlinear growth of inhomogeneities in the universe could give rise to the accelerated expansion of the universe. And so what's your take on this? Do you think that's something that makes sense, or according to your numerical investigations or your experience, if these claims make sense or not?
Well, regarding the back reaction, it's really it's an effect that arises from, well, it's a nonlinear effect. It's a nonlinear relativistic effect where we should account for these nonlinearities in the dynamical system. And this is not something that I can study with my simulation, because in our case we use what we call, well, Newtonian simulations, but so pretty much Poisson equation in an expanding universe. But it was investigated by the people in well, Geneva, now Zurich, by Julian Adamek using J-evolution. And at least in his case, there was not a strong effect from back reaction. But then we can also wonder if, well, J-evolution, has is just a particle mesh code. There is no IMR, so it's a fixed grid. So we can wonder if they do have access to the very nonlinear scales. So it's still a question, but at least with the limited resolution that, with the very limited resolution that they had, they did not see any strong effect from back reaction. So it's the first thing, and actually it's not that straightforward to know if there is a strong effect, because it really depends on even different averaging procedure. But here I was averaging over directions, over sources, but averaging over some proper area around the observer, and using well, the null geodesics. When we are interested in back reaction, we are not interested in averaging over well, this null geodesic, right? We are interested in different kind of averages, and depending on if we are doing a volume average or something even different, it really changes. So it really depends. But apparently, from the numerical investigation that there are in for the moment, there is no strong effect, but it's extremely dependent on which averaging procedure is chosen, and if the averaging procedure even makes sense. So I would say it's not straightforward.
It's not yet completely settled.
No, I mean,
Okay.
from what Julian have investigated, there is no such effect, but maybe if we go to even smaller scale, we should find something. And also, is the averaging procedure proposed in the work of, well, Thomas Buchert, is this really the averaging procedure that is very important for this study? It's not completely sure also. Even the notion of averaging chosen really depends which kind of bias we will have. So.
Okay, thank you.
Okay. Are there other questions? I don't see other raised hands. Okay, if not, let's thank again Michel-Andrès for his talk. And just a reminder that next Friday there will be the last pizza seminar of the year, which will be the special pizza seminar. And please don't forget to fill in the doodle if you plan to attend the Pika Pika. That said, I think we can close today's pizza